Good morning, sir. My name is Anushmita Roy. Today I am diving into a very important topic in signal processing, that is classification of signals. This is a core concept in electronics, communications and control systems. Whether you are preparing for exams or just starting to explore the world of signals, this breakdown will make it simple and clear. I will cover different classifications like deterministic and non-deterministic, periodic and non-periodic, symmetric and non-symmetric, energy and power signals, casual and non-casual signals, with examples for both continuous time and discrete time cases. Now the first one is deterministic and non-deterministic signals. A deterministic signal is one that you can describe completely using a mathematical expression. If I know the formula, I can tell you the exact value of the signal at any time, past, present, or future. For example, in continuous time, this is a simple sine wave with amplitude 5 and frequency 50 Hz. In discrete time, again we can predict every single value. On the other hand, a non-deterministic signal, also called a random signal, can't be exactly predicted. Instead, we describe it statistically. For example, noise picked up by an antenna or the voltage due to the thermal noise in a resistor. In discrete time, it might be a random sequence of ones and zeros from a sensor. The main difference is predictability. Deterministic signals are 100% predictable, while non deterministic ones aren't. And in real life, we often deal with both. The next one is periodic and non periodic signals. A periodic signal repeats itself after a fixed time interval. For continuous time signals, this interval is called the fundamental periods, and we say for all. For discrete time signals, the interval is an integer and we write for all. Example in continuous time is x of t equals to sine 2 pi t where t equals to 1. Example in discrete time, x of n equals to cos of pi n by 4 where n equals to 8. Now non-periodic or aperiodic signals do not repeat. For example, an exponentially decaying signal in continuous time or in discrete time. The example in continuous time is x of t equals to e to the power minus 2t ut. Example in discrete time, x of n equals to n, comma u of n. Now, in communication system, periodic signals are often used for carriers while non-periodic ones are used for data transmission. See the graph of periodic signal. The graph will repeat itself after a fixed time interval, where the non-periodic signals graph doesn't repeat over time. Now move on to the next topic, symmetric and non-symmetric signals. We have symmetric and non-symmetric signals, also called even and odd signals. An even signal is symmetric about the vertical axis. Mathematically, continuous time is x of t equals to x of minus t, and discrete time x of n equals to x of minus n. Example, the left side and the right side of the graph look identical. An odd signal or a non-symmetric signal is antisymmetric, where x of t equals to minus of x minus of t or x of n equals to minus of x of minus of n. Now, the continuous time example of symmetric signal is x of t equals to t square, and for non-symmetric signal is x of t equals to t. The discrete time signal example for symmetric signal is x of n equals to n square, and for non-symmetric signal is x of n equals to n. Now see the graph of symmetric signal. The left side and the right side of the graph look identical, and the graph of non-symmetric signal is positive on the right negative mirror on the left. So we can say any signal can be expressed as the sum of an even part and an odd part. This property is useful in Fourier analysis. Even signals contain only cosine terms and odd signal contains only sine terms. Now let's talk about energy and power signals. An energy signal has finite total energy and zero average power. The total energy for continuous time is E equals to integration minus infinity to plus infinity mod of x of t whole square dt. And a power signal has infinite total energy but finite average power. The power P equals to limit t tends to infinity 1 by 2t integration of minus t to plus t mod of x of t whole square dt. In practical systems, periodic signals are usually power signals and finite duration signals are energy signals. The continuous time example of energy signal is pulse e to the power minus t ut, and for power signal sine 2 pi 50t. The discrete time example of energy signal is 1 by 2 whole to the power n u of n, and for power signal cos 0.1 pi n. Now look at the graph of energy signals. The graph is decreasing exponential signal, and here is the graph of power signals. The next one is causal and non-causal signals. A causal signal exists only for in continuous time or in discrete time. For example, where is the unit step function? A non-causal signal exists for negative time values. Example, here the signal lives in the past. In real-time physical systems, we can't have non-causal signals because they would require future information. But in offline processing, like digital image filtering, non-causal signals are possible. The continuous time example of causal signals is x of t equals to e to the power minus t ut. For non-causal signals, x of t equals to e to the power t u of minus t. Discrete time example for causal signals, x of n equals to 0.5 to the power n un. For non-causal signals, x of n equals to 0.5 to the power n u of minus n. The real-time signals of causal signals must be causal, and the real-time system of non-causal signals can be non-causal in offline processing. So these are the 5 different classification of signals. Now we see a quick recap of the classification of signals. That is, deterministic is periodic, non-deterministic is random. Periodic repeats, non-periodic doesn't repeat. Even, symmetric, odd, non-symmetric. Energy signal finite energy, power signal finite average power. Causal exists for t greater than equals to 0 or n greater than equals to 0. Non-causal exists for t less than equals to 0 or n less than 0.